Hi everybody, welcome to this next little lesson. This is just going to get you ready for the Gizmo assignment that I've put up on the webpage. I just wanted to run through the Gizmo first and make sure you get a feel for it before you go ahead and attempt to do the assignment. So once you've signed in, once you've logged into the Gizmo class and you've come to the distance time and velocity time graphing Gizmo, this is what you're going to see. Now a few of the controls right here is where you can click on and drag, once you can click on and drag the number of points, you're able to see that on the graph to the right, you get more points to work with. If you want to move this, you just put the little hand and you drag it to wherever that corresponding distance is. So at this time, third point, if I wanted them to be at the 30-yard line, I would drag this down to the 30, and that means that the runner should be at the 30 at that point in time at 2 point something seconds, which we'll get to in a minute. So that's 1 point. If you want another runner, you click on show graph and show animation, and that'll give you another graph here and another character to run. We don't want that right now, but you can. Green starts, green can pause, green can continue, or red resets the whole thing, whether they're running or not. This little triangle gives you the hand button. Top or bottom, you can drag it to find out where they would be at any given time. So if I want to know where they're going to be at exactly 2 seconds, and I can't quite make it out on the graph for whatever reason, that shows me they should be at the 20-yard line at 2 seconds. This is just past 2 seconds and they're right at the 20, so I can kind of answer questions that way. There's a few other things that we'll get to when we're there. For instance, we can look at a velocity time graph by clicking this button, or this tab rather, or the distance time graph on this tab, but for now we want the controls. So that's basically a quick overview of what you're going to do. I just want us to just click play, watch this graph and watch the runner. What we're going to try and use this for is to get you an idea of how to correlate what we graph here with what the actual motion is down at the bottom, and this Gizmo is really good at doing that. So the first thing I want us to notice on this graph is what's on the axis. What am I graphing? Your time almost invariably will always be on the x-axis. So here's my time. It's in seconds because we're using a stopwatch, so we have seconds. Up the y-axis is whatever I'm graphing versus time, so in distance time, velocity time, displacement or position time, whatever we have. Now this is very descriptive. Distance from starting line in yards. Remember, we always put our units in the brackets. So the distance from the starting line, as soon as I hear from the starting line, that gives me a relative position. That gives me a starting point, and that means that it has to be a vector quantity. Scalars don't give us any reference. They don't care whether you're running forward, backwards, sideways, or on some sort of an angle. They just care what the distance is you move. This one says from the starting line, and so we can see if this is 0, because that's the starting line, 0, any of these little markers are indicated here at 10, 20, 30, and 40. So this graph is going up. It only moves in one direction. That means that this runner only moves forward. Forward is a direction. There's our vector. So at time 1, our runner is at the 10-meter line, but the 10-meter forward. If it was distance and it just said 10, this guy could have run backwards, and while that's still 10 meters or 10 yards, that's not helping him win the race. And so that's the first thing. The other thing is, as this guy runs this time, I want you to watch the speed. You'll notice that it's constant. The runner is running the same speed between each one of those little markers the whole way along. And that corresponds to this straight line here. The slope of my graph is going to be how fast the person is moving. It's the rate of change. If you remember your slope, y equals mx plus b, we take the rise over the run and we can calculate all those fun things. Well, the rise over the run part of our graphing, the rise is this way and the run is that way. Well, if we look at any point here, I'm just going to take between 1 second. So between 2 and 3 seconds, we have 5 squares, and we go up 5 squares. Between 0 and 1 second, I go over 5 and up 5. Between 1 and 2, 5, 5. You see each one of my intervals, no matter what I take, if I take the same amount of time, they move the same amount of distance. And so this runner is moving constant. So a constant speed because it's got a straight line. Let's have some fun with this guy. We interpret this because we're kind of programmed to interpret that as like a race, a 40-yard dash. It doesn't have to be, it's just marking stuff off for physics, but it could be. Let's do something fun. Let's have them run all the way to the finish line in 1 second. That's really fast. Usain Bolt would be proud. But this guy's not the smartest runner, and so he decides that he wants to run back towards the starting line. Alright, now if I do that, it's not going to end up back at the starting line, but he runs at basically the same speed here. So what I want him to end up at the starting line. Now if he does come kind of like this, that's not the same nice straight line. So I just want to adjust these so I get roughly the same slope between each one of my points. It's not always perfect. I want a straight line there. That's pretty good. So this straight line tells me you should be running roughly a constant speed backwards. So we should sprint really fast, really steep line, fast to the start, or fast to the finish, and then back to the start. So just to see, I'm going to push stop here, reset everything, and have my runner move. Sprints fast, much slower, but yet constant speed. So the slope, depending on how steep this line is, tells me how fast the person is running. So this tells me that it's very steep, very quickly they move a lot of distance up in not a lot of time over. So they have a very steep slope, runs fast, and because it's up, they run forward. Now they turn around and they run backwards because they're going down. This graph's going down. So they're going from the 40 yards away from the line back towards 0. So they're running from 40 back to 0. And so this fact that it's going down tells me that the direction is backwards. And the fact that this takes some time, because this line is not nearly as steep as that one, they're running slower. So the run is slower going backwards. And that has some very interesting implications. It's different than what we just saw. We have an up and we have a down. That tells me my direction because this is the position relative to start. Are you going forward or are you going backward? But the distance traveled is he went 40 yards this way and then 40 yards backwards. So the total of that is 80 yards. And yet, if I look at the start and the stop position, it's 0 and 0. And if you just kind of blinked your eyes and looked back here 4 seconds later, it looks like you didn't move, which is a weird thing with a position time or a displacement time graph. If you go to the distance traveled, you'll notice it's all positive. It all goes up because distance traveled, there's no mention of the starting line. It doesn't care about the starting line. It just says he went 40 in 1 second and then another 40. So they finish off at 80 yards right here, 80 yards after 4 seconds. So this one person went 80 yards. You'll notice that the slope here is very steep. The slope here not as steep, but this one is positive. This one is going up while this one's going down. Well, the reason is in a distance time, we don't have the direction. There is no negative distance. I can't unwalk. I can't unrun what I did, which is what you'd be saying if you drew the line this way on a distance time. So if you get one of those pedometers in your special K box and you walk around all day, it doesn't matter if you walk away from your house or back to your house, it's going to count up. It's just going to add your steps. That's distance. But your displacement, if you're talking about how far away you are from your house throughout your day, if you walk to school, you're really far away. On your way home, you're getting closer. And so depending on what time of the day you look at, you'll be a certain distance away from your house, which is this graph, vector. The velocity time graph, this is kind of different. It's kind of a next level we'll get to in the next lesson, but it shows you how fast you're running. So all I wanted to do was just point out a few of those key things. The difference between a distance time, always positive, and a velocity time, positive and negative, and the controls. So at this point, I think you're set. We'll let you go and you'll do your assignment, and then we'll come back. We'll have another video with this where we're going to look more at this velocity time graph and how does that relate to everything.